Okay, period 7, you're going to be seeing what period 8 is like. I'm sorry for this. To start, I want you guys to put a grid down, or put an axis down, just a coordinate axis, and we're going to graph two functions. Y equals 2 to the x, and its opposite, or inverse, y equals the log base 2 of x. The right one is often called a binary log. The left one is about your most basic exponential function you can do. However, like I've hinted to you, it is not the cleanest exponential function that you'll ever graph. The cleanest one will be one that's y is e to the x that we're getting to in the next chapter. But y equals 2 to the x is easy to understand. It's the doubling one, that every number is double the one that came after or came before it. And if I start at 0, 1, which I know is an ordered pair, that acts as like my middle ground. So I can go right to that and watch my numbers get crazy big. If I graph it, I'm just going to go 1, 2, 2, 2, 4, and I'm already off the grid. If I go left, my numbers get small really quickly. 1/2, 1/4, 1/8. And this is essentially how the graph is going to look. Now, you can see why it's really ridiculous to graph this on a normal grid, because you really can't draw it that well. But if I flip my ordered pairs around, so take every xy that you just did and graph it as the opposite. So 1, 0 becomes 0, 1. 1, 2 becomes 2, 1. 2, 4 becomes 4, 2. Negative 1, 1/2 becomes 1/2, negative 1. Then you have 1/4, negative 2, 1/8, negative 3. And you get a graph that looks like this. This is equally as important of a graph. And this is the graph of y is equal to the natural log, or sorry, to the log base 2 of x. Instead of being a function that grows without bound, this is a function that in some ways will start to get smaller and smaller and smaller. It does grow, and it continues to grow. It will get larger and larger, and it will eventually hit every y value, but it does so at a much slower rate than the one that came before. Later on in calculus, we have a concept called concavity that describes how fast the rate of change of a graph is changing itself. This one is what we call concave up, because it is going increasingly higher. Its rate of change is increasing. It's not only getting larger, it's getting larger faster and faster and faster. This one's still getting larger, but it's getting larger slower than the other one is, and I think you can see that. The line that I want you to graph in the middle of these is y equals x. And I'm just going to put it as a dotted line. This is the graph of y equals x. And you may notice something about this graph. What is it relative to these two? Equidistant. There's a word I'm thinking of, Simba. It's a line of symmetry. This is a symmetrical line, or it's a line of symmetry, and that's basically all inverse functions have. If y equals x is a line of symmetry, because you have flipped your x and y ordered pairs. So this is just a basic sense that's going to give us more of a thing to do 2 days from now when we start really graphing these. But graphing is going to be a big part of both this chapter and the next one. You should be able to graph any exponential function and its inverse. Okay, we're going to shift gears a little bit, and we're going to do a couple of examples of stuff from the last couple of days. Yes, Tom?
So for like the y equals 2 to the x, is that like you could put it as f of x equals to the x, and
yeah.
For the log x it would be
f inverse, yep. Yeah, we could say that this is really f of x, and I could say that this is f inverse of x, or I could flip those around, make the other one f of x and the one before it f inverse. F inverse of x is just a notation that means its inverse function. It's a special notation that relates the two of them. Okay, number one, to review. You guys need to take any number and raise it to any power. So if I take negative 7 to the negative 4/3, that is something I would expect you guys to know how to do. And what we have done is we've broken that up into 3 parts. When you have an exponent that has a negative and is a fraction, I'm going to say negative 27, but actually raised to the, I could do negative 1 first. Why don't we do 1/3 first? And then the fourth, and then the negative 1. That way I only flip it in the very end. So negative 27 to the 1/3 is third root of 27. Remember, you can do a cubed root of a negative number. Just 3. Not 3, but negative 3. So they have negative 3 to the 4th to the negative 1. And then negative 3 to the 4th, 81. And then 81 to the negative 1, 1/81. Second problem type came from a couple nights ago too. 7x to the negative 3/2 equals 189. And just that presence of that 7 as a coefficient means there's a first step that you can't get around, which is divide by 7. So you get x to the negative 3/2 equals 187 divided by 7, 27. Then to undo raising to the 3/2, negative 3/2, you have to do something to the other side. Raise to the negative 2/3. Be careful, because that's going to change everything if it's not negative. Makes it so that I have x is equal to, and we know that this can be expressed as 27 to the 1/3, then squared, then negative 1. Or x is equal to, can you do that without writing them all down? 1/9. You have problems that are going to ask you to write in exponential form. So let me kind of show that here. This is a radical. I'm trying to get in the habit of drawing my radical last so I don't draw it and then have to redraw it. I'm going to want you to take this and put this in exponential form. When you put in true exponential form, you don't care if the exponents are negative or positive. You just want them listed out. So this is much easier than it seems. But there is one change you may want to make before you do anything. 32 should be written as a power of a simple base. To the 5th, x to the negative 11th, y to the 6th. So if I'm going to write this, it's 7 times, oh, thank you. 7 times, we have 2 to the what? 5/4. And just leave it like that. X to the negative 11/4, and y to the negative 3/2. Turn off the grid. Next one, root 32 times the 5th root of 64. And I want this in radical form. I'm going to pause for a second. To do this, you need to convert them both into exponential form. So 32 needs to become 2 to the 5th times the 5th root of 64 needs to become 2 to the 6th. Now, rather than simplify the radical at this point, we're going to bring them to exponential form. 2 to the 5/2 times 2 to the 6/5. That is not 4 to the anything. Do not make 2 times 2 be 4, because that's not 2. It's 2 to a power, 2 to a power. So the total number of 2's has to be 2 to the 5/2 plus 6/5. You guys all know how to add 5/2 and 6/5. Yes, you do. 2 to the 37/10. And since that's 2 to the 37 tenths, that is equal to the 10th root of 2 to the 37th. And there's 3 groups of 10 in there, so this is going to come out as 2 to the 3rd 10th root of 2 to the 7th, which if I simplify is 8 10th root of 128. Okay. Number 5. Simplify 10 to the root 2 minus root 3 times 100 to the root 3 minus root 2. The first one, like, you can't do anything with. It's 10 to the root 2 minus root 3. The second one, though, is 10 squared to the root 3 minus root 2. Key there is moving the 100 into a base of 10. And then you get 10 to the root 2 minus root 3 times 10 to the 2 root 3 minus 2 root 2. Now you actually end up with 10 to the root 2 minus root 3 plus 2 root 3 minus 2 root 2. And then just hunt for your like terms, and you're going to get 10 to the root 3 minus root 2. Okay, last one. 27 to the 3x minus 2 equals root 3 over 3 to the 5x plus 1. Also pause. Come on. 2. Boop. Okay, so let's focus on the root 3 over 3 part. That one is not good. It's not good form to see what I need to do with it. But if I remember that root 3 over 3 came from 1 over root 3, and how would you know that? Well, because you've done 1 over root 3 so many times, or 1 over root 2, or any of those, that you may recognize that if I multiplied by root 3 over root 3, I would get root 3 over 3. But I don't want to do that. I want to keep it as 1 over root 3 for this problem. So I'm going to rewrite the problem. 27 to the 3x minus 2 is equal to 1 over root 3 to the 5x plus 1. In that form, you can now write both sides as simple bases. 27 is really 3 to the 3rd to the 2x minus 2. Do you know what 1 over root 3 would be? 3 to the 1/2. And you get 3 to the 27x minus 6 is equal to 3 to the negative 5 halves x minus a half. 3 times 3 is definitely 9. And you end up with 9x minus 6 is equal to negative 5 halves x minus a half. Multiply both sides by 2. 18x minus 12 is equal to negative 5 halves x minus 1. Or 23x is equal to 11. Or x is 11 over 23. And we're done.